Now let's look at some examples of the derivative as a rate of change. Notice it doesn't say as an instantaneous rate of change, because now that we know the derivative is an instantaneous rate of change, we'll usually just call it rate of change. And we have a problem. It says estimate g prime of negative 0.5, where g of x equals 2 to the x plus 4. Now, when you want to find the derivative at a point, we have a shortcut method where we can pick numbers that are equally spaced on either side of our number of interest, our x equal to a or x equal to c, and we want to pick them close and then use the slope of the y values at that point. So at negative 0.5, I could do negative 0.4 and negative 0.6, but we should get a little bit closer when we have decimals. So let me pick x values, say at negative 0.51, think of this as 50, and negative 0.49. And we need to find the y values or the g values that go along with those. I don't need the point in the middle. I'm using the shortcut method, which says pick a point close to it on either side and just use those two numbers and get the slope. So if I plug this point in, I'll have 2 raised to the power negative 0.51. And when you put those in a calculator, be careful with the negative sign. You can use it in the calculator, be sure to use parentheses. Or you do it in Excel with a formula, but watch the use of parentheses to be sure your numbers are accurate. If I plug this number into the formula, I get 4.702222, and some more decimals. This is 2 decimal points. I might be able to stop at 2, but typically do at least 2 more. And so I decided I'd go ahead and do 6 decimal places there. If I plug negative 0.49 in, I get 4.712025. I did another 6 decimal places. And I'm now going to do the slope between these two numbers. So my derivative, g prime of negative 0.5, and I'm saying equals even though it's an estimate, because we could get perhaps slightly different numbers if we choose closer or numbers further away from negative 0.5. So this is an estimate. And I do the change in y over the change in x. So if I go, my biggest y, 4.712025 minus 4.702222 over negative 0.49 minus negative 0.51. When I subtract, I get 0.0098026, just a little bit further than 6 decimals, over, and this would be 0.02. And when I divide, I'll end up with 0.49013. Move my 2 decimal points over, my 2 decimal points. And this is the value I get for g prime of negative 0.5. That would be considered the slope of the tangent line or just the instantaneous rate of change at a point. Now let's look at another example where we just start off with a data table, but it will also ask an additional question. Here we have a data table already up here for this problem. Find f prime at 0.9, and is f of t increasing or decreasing at that point? So let's look at the first part of this, find f prime at 0.9. So my point of interest is here, 0.9. That's the point that I'm looking for. Now for the shortcut method, we pick something equally distant on either side, and we see that our data table does have 1/10 of a unit this way and 1/10 of a unit this way. I can't get closer. I can only work with the data I'm given. So let's use these two values for F and those two values for T to set up our rate of change to find F prime of 0.9. So let's make the denominator positive. X is 1, X is 0.8. Let's go 1 minus 0.8. It's always a good idea to have the denominator positive, and I tend to put the X's in first if I think about it. 1 goes with the value negative 6.4. Minus, with 0.8, we have negative 7.3, so it's minus a negative 7.3. Negative 6.4 plus 7.3 gives me 0.9 divided by 0.2. And 9 halves is 4.5. So 4.5 is the instantaneous rate of change. It is the derivative. It is the slope of the tangent line at this point. Now, I need to decide if the function is increasing or decreasing. So remember, derivatives as a number tell us information about the function in words. So this number is greater than 0. It is positive. If you think about it as slope of a tangent line, a positive slope means the line goes up. It increases. Increases. That's the answer to our question. So F of T increases at at T equal to 0.9. So somewhere, wherever 0.9 is, my function is increasing at that point. Now let us look at an example from economics. We just saw an example where we need to work with a rate of change in economics. It asks for the marginal profit. If you think back in Unit 3, we talked about marginal analysis, marginal revenue, marginal profit, marginal cost, which is a rate of change in economics or business. Rate of change of a function with respect to quantity, selling one more item or producing one more item. So we need to find out marginal profit. And if you think back, profit is revenue minus cost. So we're given the cost function, C of Q is equal to 3Q squared plus 50Q. And our revenue function is 200Q minus 2Q squared. And profit equals revenue minus cost. So we put the revenue function in first. Revenue is income. It always goes in first because you hope it's bigger. So let's put 200Q minus 2Q squared minus, and now for cost, I'm going to put the cost in a parenthesis, 3Q squared plus 50Q, because we have to be sure that we subtract everything that's cost. So let's go with the negative 2Q squared first, higher power first. Negative 2Q squared minus 3Q squared is negative 5Q squared. 200Q minus 50Q is a positive 150Q. So this is our profit function. Now remember, when we go to find a derivative, we do the slope and we use the original function, the y values. So if I want to find marginal profit at 12, I need to do the profit values at an equally spaced Q value on either side. On either side of 12 would be 13 and 11. So let's find the profit at 13 minus the profit at 11, and then we'll divide by 13 minus 11. It's still slope. So the profit at 13 is 1105 minus profit at 11 is 1045. I just plugged 13 in for Q, and then I plugged 11 in for Q. And then 13 minus 11 is 2. So when I subtract and divide, I end up with a positive 30. Well, so I need to interpret that. What does that mean? Marginal profit is 30. That would be $30, because it was dollars in the numerator, profit in dollars, per, and our 2 was units, so it's per 1 unit in the denominator. $30 per unit is the marginal profit, which means profit increases $30 for 1 additional unit sold. So my profit is increasing $30 more for the next one that I sell. So let's look at marginal profit now at 17. I find the profit at a Q value 1 on either side, has to be equally spaced for the shortcut method. Profit at 18 minus profit at 16 divided by 18 minus 16. Profit at 18 is 1080. Profit at 16, 1120 divided by 2. And notice here a problem. When I subtract, I get a negative numerator. Divided by 2 gives me a negative 20. Well, what does that mean? Okay, this is still $20 per unit. And so that tells me now that profit decreases $20 for 1 more unit. And this is 1 more unit after 17. So the marginal profit at 17 is going down. Doesn't say profit is negative. This is not a loss. It's just the profit is not as big as it was before. And over here, profit is increasing at 12. Well, let's think about that visually. What is that going to tell us? At 12, profit is increasing. At 17, profit is decreasing. Well, if it increases and then it decreases, somewhere here in the middle, I must have a maximum profit. Profit's increasing, I hit a number, and it starts decreasing. I have a maximum. Our profit function here is a quadratic. So if profit is a quadratic, I know how to find the vertex. The vertex is the maximum point if I have a parabola. Parabola vertex, the x value is negative b over 2a if it's in the form y equals ax squared plus bx plus c. So let's do that. For this problem, I don't have x, I have q, equal to negative b. Well, my 150 here is my b, so that's negative 150, over 2a. A is negative 5. 2 times that would be negative 10. So my q value is 15. So at 15 units sold, profit is maximum. So you plug in 15 in here and you'll find out what your maximum profit is for this particular function. We're going to look at another application in economics, elasticity of demand. You saw this back when we did the unit on business terminology, and we're going to go into additional details here. We defined elasticity as percent change in demand divided by percent change in price. And we said that if the absolute value of elasticity is less than 1, demand is inelastic. Now, elasticity itself is always a negative number. Percent change in price we usually talk about as a 1% increase. And when prices go up, demand goes down. So that would lead to a negative numerator and gives us a negative value for eta. That's why in math, we work with the absolute values. The absolute value less than 1 would mean a fraction. And for elasticity to be a fraction, if we have a change in price at a certain percent, the numerator must be smaller to have a fraction less than 1, and it would be a negative number. If the absolute value of eta is greater than 1, we call it elastic. Where if we have our fraction, then whatever the denominator is, the numerator must be higher to get it greater than 1. And we have elasticity equal to 1, where it's unit elastic, and that tells us that it's about the same percent change in both. Well, now that we've had derivatives, what we can do is take that percent change and turn it into rate of change. And all that's gone through in the lesson and shows you how you get from a percent change to a rate of change with some little algebra tricks. So that we end up with saying, okay, suppose the demand function is Q as a function of P. A demand function, remember, just relates Q and P in an equation. So if we take the derivative of this, that is our rate of change, the derivative of a function named Q is Q prime. And the formula for elasticity, if this is the way the function is given, is eta equals P over Q times Q prime. But a demand equation could also be written as P equals a function P of Q. And the derivative of a function P equals would be P prime of Q. And because of the way the percent change turns into a rate of change, in this case, elasticity is P over Q, but then it's times 1 over P prime. So depending on the way your original function is written, you have two different formulas you have to use to find the elasticity for a function. And we are going to look at a couple of different problems, one of each, so you get some practice using both of those types of formulas. For our elasticity problem, we're given that the demand equation is Q of P equal to 100 minus 2P, and we want to find out where demand is inelastic. Remember that for demand being inelastic, it means that the absolute value of eta is less than 1. So we'll be working with absolute values and inequalities. First, we need to find eta in here. We had two possibilities for formulas. This is Q of P, so we need to think about, if I take the derivative, it's Q prime, so I want to use the formula where eta is equal to P over Q times Q prime. And what we will do is say P is P. I don't have a value for P in this problem. Q is Q, but Q is this whole expression here. Q equals 100 minus 2P. So all of that goes in the denominator. Well, now we get to Q prime. Have to use the derivative of this. Now up to this point when we've found a derivative, we've taken a point on either side of a number. We don't have a number. We're looking for the elasticity function. But look at this and think about y equals mx plus b. This is actually b plus mx. This is a linear demand equation. So if it's a linear equation, then that means that the slope is the derivative. Remember that the slope is a rate of change, and the rate of change is the derivative. So the derivative is the same as the slope, and the derivative here then is negative 2. So I'll multiply this times Q prime, which is negative 2. So elasticity is negative 2P. Remember, when you multiply by a constant, you don't multiply the denominator, just the top. Negative 2P over 100 minus 2P to solve this problem to find out where demand is inelastic, we take the absolute value of that less than 1. Now, I can't solve an equation or an inequality with an absolute value symbol in it. I have to remove the absolute value. So let's think about that a little bit. I'm working with P's and Q's. P is a price. This number P has to be positive. It's a price, that's dollars. 100 minus 2P, that's Q. Q is a quantity. That has to be a positive number. So the P and the denominator are already positive. The only thing the absolute value does is take this -2 and make it +2. So to remove the absolute values, I have 2P over 100 minus 2P is less than 1, always. Since Q is positive, I can multiply it on the other side, and I'll have the numerator 2P less than 1 times 100 minus 2P. Add 2P over here gives me 4P less than 100, so P is less than 25. So any prices that are less than 25, if I plug into my elasticity function, will be the demand is inelastic. Now, we know that P has to be greater than 0 because it is a positive number, always. But we also are talking about Q's here. So are there any other values that we might get for P? Possibly, but Q has to be positive, so let's look at that. Suppose Q is a positive number, which it has to be. Q is equal to 100 minus 2P, so I just substitute, which means -2P is greater than -100. Inequality, if I divide by a negative, it switches the direction. So P has to be less than 50 for Q to be positive. So for inelastic, the prices have to be less than $25, but P itself could be anything up to 50, so that would indicate that perhaps between 25 and 50, demand will be elastic. So that gives us a little bit more information about the other possibilities that we have for elasticity. Now let's go look at a second example where I have P as a function of Q. For this elasticity of demand problem, we're given our demand equation as P equals 100 minus e to the 0.1 Q. So that if we're using the formula for elasticity, eta equals P over Q. When we get to the derivative part, here we'd be taking the derivative of the function P, which would be P prime. So we use the formula where this is times 1 over P prime. Now when I look at that function, that's not linear. It's going to be a little more complicated finding P prime. We are interested in the elasticity at Q equal to 40, and to find a derivative at 40, we'll use the shortcut method and find values the same distance on either side of 40. I think I'll just go 1/10 of a point. So if I have a Q value at 39.9 and a Q value at 40.1, let's find the P values that go with that in order to find P prime using the shortcut method with the slope formula. So if I plug 39.9 in for Q, this is one of those occasions where Excel can be very helpful because you only have to type the formula in one time. I'd multiply 0.1 times 39.9, do e to that power, subtract it from 100, and I get a value of 45.9451. I plug 40.1 in for Q, go through the same process to get P, and P is 44.8 0.8531. And I'll use the slope formula on this to get my value for P prime. So that P prime would equal, let's go in the denominator, 40.1 minus 39.9. And in the numerator, 8531, that goes with 40.1, minus 45.9451. And that will give me the derivative, and I should have written this a little bit differently, the derivative P prime at 40. Because remember that to find the derivative at 40, we pick points on either side. So this is the derivative at 40, and it turns out to be a negative, numerator smaller, 5.46. So I'll round that to 2 decimals. So this is what the derivative is equal to. Now I have to go back to the formula. So eta is equal to P over Q. Well, my Q value is 40. Now I could put in the whole formula for P, or I could come back up, especially if I used Excel, and say, okay, so really what was that value for P when I plugged in Q equal to 40? So if you plug 40 in for Q, you end up with 45.4018. That's my P value. That is the numerator. Multiplied by 1 over P prime, which is negative 5.46. Do all that multiplication and division, and I come up with negative 0.208. This is the value for elasticity. Now remember, elasticity has no units, so I don't have anything to put on the end of that. So what does that mean? Well, my elasticity here, if I take the absolute value of eta, I get a positive 0.208, which is less than 1, which means elasticity is inelastic. Well, so what does that mean? Well, think back about elasticity. If we think of it as the word definition, percent change in demand divided by percent change in price. If I have this as my fraction, I can think of it as that over 1. So for a 1% change in price, and that's an increase, this has to be the numerator. So I have a negative 0.2% change in demand. So if price increases 1%, demand is only going to drop 0.2%. So that's how our inelastic problem gives us actual values we can think about as, suppose I raise prices 1%, how is that going to affect demand? A very small change in demand.